Welcome back, grade 12 learners. This is the third video on differential calculus, and this is part 3. And we're going to look at sketching of curves of cubic functions. This is also an application of differential calculus. We'll focus first of all just on how to sketch cubic functions. Part 3, sketching of curves of cubic functions. First of all, we're going to have a quick revision of some content skills relating to what we've done in video lesson number 1 and video lesson number 2. And then we're going to give you just an overview of turning points, inflection points, and concavity. Then we're going to go into sketching of curves of cubic functions. And then as usual, that you'll have an exercise worksheet to practice these skills. Let's do a quick revision here. Differentiate that for me. Give you a chance. 1, 2, 3, 4, 5 examples and 30 seconds each. Let's start. You only have to write down the answer. You don't have to write down the given expression. Okay, first one. That's right. 6x squared plus 18x plus 14. The next one, negative 9x squared plus 10x minus 16. Next one, 12x squared minus 22x minus 2. Next one, be careful here, negative 3x squared plus 2bx negative 2a. And the last one, 3ax squared plus 2bx plus c. Okay, now we're ready. Also, what you're going to need here, let's just see whether you still remember how to use your calculator. There's a few expressions, and I'd like you to try each one, and with your calculator, less than a minute for each one. Just write down the solutions. That's right. Now, let's see. That's correct. x1, x equal to 1, x equal to negative 4, x equal to negative 6, x equal to negative 6, x equal to 2, x equal to 1 over 3. And we're not surprised. We have coefficient there of 3, so I expect to have thirds here. Here we have x equal to negative 5, x equal to 2, and in this one you notice there are two distinct roots, but one of the roots is duplicated. This one here, again, here we can see we have a 2, so we're not surprised to get halves, in this case 5 over the 2. The last one, this one is an example where we only have one real root. The other roots of this cubic key are non-real. So those are the main skills that you will be requiring in sketching curves of cubic equations. Let's just go over what we've done previously. The gradient of a tangent to a curve. Let's start off with a quadratic function. There we have a quadratic function, and I have 3 points on this quadratic function here. We have A, C, and B. If I look at B, I have a tangent there. What is the gradient of that tangent? That's correct, right? That is a positive gradient. And if I look at A, there we also have a tangent at A, but the gradient of that tangent is negative. So on the left side we have the negative tangent, negative gradient, and on the right side we have a positive gradient. At C, at point C, the turning point, there we have a tangent, but the gradient here is, that's right, the gradient is 0. It's parallel to the x-axis. So we see in this quadratic equation, the gradient changes from negative, then it is 0, and then it changes to positive there. At B, as we said, it's positive. At A, it is negative. Gradient at C is 0. and gradient there is m. In this case, this is a way of simplified way of writing it. M greater than 0, and m equal to 0, and m less than 0. But gradient can also be written in terms of the derivative. That means the derivative, first derivative is 0. The first derivative is less than 0 or negative, or the first derivative is equal to 0. Okay. And at C here, at C we have a turning point, and the turning point can be determined by finding the first derivative and equating it to 0. And this is the most important concept that we're going to use here. How to determine a turning point? Determine the first derivative, equate it to 0, and then you solve the equation. Let's look at a cubic function. If I look at this curve here, we see at point A, we have a tangent here, and this tangent, the gradient of that tangent is 0. The gradient of that tangent is 0, right? There we also, but this is not a tangent, right? If we look at this tangent here, we notice that this tangent, the tangents here are always above the curve. If we look on this part here, we see the tangent here is always below the curve. So somewhere it changed from being above to below. And that place where it changes from being above or below the curve, this point here, this is a new point we're going to use, and this we refer to as the inflection point. Let's look at that now. At A, we have what we refer to as a local maximum, right? And that local maximum we can determine by finding the first derivative and equating it to 0. Then at B, we have a local minimum. And that local minimum, we also can determine the first derivative and equate it to 0. Okay. Then at C, there we have an inflection point. And to determine the inflection point, we'll find the second derivative and equate it to 0. Now, you must have been wondering why we say local maximum. You see, here, in this locality, it's a maximum. But if I follow that curve, there's actually a true maximum, or there's other values more than that, right? So that's why we refer to this as a local maximum, or this one as a local minimum. There are values there, right? This other value, if we want to, there's actually a true maximum somewhere there, or a true minimum somewhere there, or we also refer to this as the absolute maximum or the absolute minimum. Next, we're going to look at the intervals where a curve increases or decreases. Let's look at this curve here. What do we say is this point? That's right, that's a local maximum, and that's a local minimum. Now, if I look at this local maximum and the local minimum, there's a corresponding x value. And that corresponding x value with the local maximum is at A, and the corresponding x value for the local minimum here is C. We refer to these two values at A and C as the critical values. At x equal to A, there's a critical value at x equal to C. Now, if we follow this curve here, just follow the pointer. See what's that? The curve is the function value is increasing. And then if we follow this, we see the function value is decreasing, and then it increases. So this, at the local maximum, that's where the change takes place. You see, it's increasing, 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 and then it is 0. Then it decreases and decreases. So these two critical values will determine to you where a curve increases and decreases. Can you now remember where we have the increasing parts? So you want to look at increasing, and the increasing is where the gradient is positive. So let's look at, there's the increasing part. You see, there are two parts where it increases. Now, how do we write this down? So we need the critical value. It increases there. In other words, I want x value. So this extreme x value there is at negative infinity up to A. And this one again is from C up to positive infinity. And that is the recommended way in which you should try to write your intervals there. You can see that's a starting and an end. It starts and it ends. So an interval always needs a starting and an end point. And remember, these are excluded, so never use a square bracket. So you'll have the round brackets there. So it's from negative infinity to that critical value, and from C to infinity. Let's look at the decreasing portion. Let's focus on the decreasing, and there we have the decreasing. See, I've color-coded it as well. That's the green part there. So it decreases from that critical value to that critical value, and it's quite easy to write it in interval notation from A to C, right? And the A is excluded and the C is that's open there. And there we have the two combined there. So you can see the yellow there represents the increasing, and there's increasing, and that's decreasing there. And associate increasing with the first derivative as being greater than 0, or decreasing is where the first derivative is less than 0. In part 4, we're going to do a lot more of these inequalities. Now there's another concept that we're going to look at, and this is the concavity, the curvature, of the curve. Let's look at a cubic function. There's a cubic function there. Now, what did we say was this point? That's right. This point is the local maximum, and that's the local minimum. And what was this new point? You still remember? That's correct. This is the inflection point. This way, they talk about there's an inflection taking place. In other words, the curvature, you see this there, the tangent is above, and somewhere here, if I have to draw a tangent, the tangent will be below the curve there. And the corresponding x value that goes with this inflection, in this case, let's say it's at point E, right? Now, if I look at this portion, the portion on the left side of the inflection point, right? You see this one here? If I follow that, can you see there? There's the inflection point. It then turns, and it seems to be going down. And this type of curvature, we refer to this as curving downwards. Actually, the arrow can help you there. You can see this arrow from there. It just seems to go down there. So this is concave down. Let's look at the other one. There I have my inflection point. And this one there it turns, and then it goes up. And this is what a concavity or curvature up, concave up would look like, right? Let's put that down. Concave up would be this yellow. See, that's the yellow. That's the concave up. And then concave down would be that one there. I've coded in yellow and green. And the concavity has to do with the inflection. And if I look at the critical value there, in this case, it's on the right side of the inflection. That's the greater. And on the other side, so the concavity separates the inflection point will determine where it curves up or where it curves down. So the second derivative less than 0 would be concavity downwards, and the second derivative greater than 0 will be the concavity upwards there. And how do we write the up? You see there, it's from the inflection, and it just goes this way up to infinity. And downwards again, it's from negative infinity. See, there's negative infinity up to the inflection point's critical value there, right? And these are two open intervals. So for concavity, we have to look at the critical value of the inflection point. Let's just see whether you can look by just looking at the graph, determine whether this is concave up or concave down. Let's look at that one. You can see there, just look at the arrows even there. You see, this is a nice, there's a nice U shape. This is concave up. Let's look at this one. Just look at it carefully. If this is the inflection point, you see it curves, and this one is not going that way. It's just curving like that. So this is a concave down there. This one here, concave up or concave down? That's right, it's both. So we have a inflection point here. You see there it curves upwards, that's concave up, and this one on the right side is concave down. So there's an inflection, there's the inflection of the curve, right? Then this one, if I have that point, this one is just going up, so this is a concave up. So you don't always have to have a U shape. This could just be the left side of it there. And this one, that's correct. This is one with two. You have concave up, so where within there the inflection point, there's the local maximum and the local minimum, and the inflection is somewhere there, right? Between the two. So this one, this part here is, which one is this? That's right, concave down. And this one here, just follow that turning point and the arrow, it's concave up. This one, let's look at this. There, this one is just going like that, right? So you can even see there, this one is going concave. That's right, concave. Now we're actually going to start with some sketching of cubic functions. But let's see what is the procedure that we're going to do. Any type of sketch, we're going to have always to try to determine the y-intercept, right? Then after the y-intercept, the x-intercept or intercepts, right? Sometimes it's more than one. Then we have to determine where if there is, whether there are any turning points. And then now we're going to introduce another point here, and this is the inflection point. Let's go back now again. How do we determine a y-intercept? That's right, we let x be equal to 0. And the x-intercepts, y is equal to 0. And this is where you're going to use your calculator to determine the x-intercepts. Turning points, what do we say about turning points? The gradient would be 0. That means the first derivative should be 0. We can then solve that equation, and then we will, the inflection point is where the second derivative is going to be equal to 0. You see, this is where the calculus is going to come in. But before, we're going to look at 3 examples, but I'd like you to do it with me. I'd like you to take 3 pages there, and I want you to draw a system of axes. Because it's important here that you have at least some scale. So you, in the middle of your page, draw a line on one of the lines of your page. And I suggest you mark this off in centimeter. Don't put any numbers down there yet. Just put the ticks. So that will be 1 centimeter, 2, 3, 4. And this side here, you can just use your lines of your page. Do not mark this off in centimeters. So prepare 3 systems of axes like this, right? Don't put any values. We'll just use them there. So you can do it with me. So on the line, one of the lines of your page, and use preferably centimeters. And then here, just also, you don't have to use centimeters. The width of the lines is not exactly a centimeter. Just take the marking on the lines there. So you need to have 3 systems of axes to continue here. And I'd like you to do it with me. We're going to look at 3 examples. Let's look at the first one. Just be careful here. You can see in this case I've got a negative, so just be careful. What's the first thing we need to determine? That's correct, the y-intercept. What is the y-intercept? How do we determine the y-intercept? Let x be equal to 0. So that should be 0, that should be 0, that should be 0. Grade 12, it's embarrassing if you put this in the calculator 0, 0, 0, and then get a. You should immediately see 0, 0, 0. So the y-intercept is 0 and negative 28. Remember, you're in grade 12, not grade 0. Then the next thing that we have to do is determine the x-intercept or x-intercepts. And here we're going to use our calculator. Doesn't matter which one you use, which calculator you're using. So we expect at most 3 x values. Using your calculator, I give you a chance. Try to find them. You can even write this in factor form there. So the 3 values that we obtain is -1, 4, and 7. And we just write it in coordinate form, right? -1 and 0, 4 and 0, and 7 and 0. So whichever method you use to find this, those are the three x-intercepts. Then we need to find the turning points. How do we get the turning points? Determine the first derivative. Come, let's try the first derivative. Write it down. Come, let's check whether you have it right. First derivative, and we equate it to 0. So there, that's right. It's negative 3x squared plus 20x minus 17. What type of expression is this? Quadratic. If you want to solve it, we've got various techniques. What's the basic one? Try to factorize. If that's a bit of a challenge, you use the quadratic formula. But with some of your calculators, you can determine the x values quite easily, and either using the factor method, or there you can get your 2x values. Remember, we're not surprised to get thirds, because there I see there's a 3 there. If you get 17 over 2, oh, just be sure you are making a mistake. It's not possible. If there's a 3, you can't have something like 17 over 3 or 17. You can't have 17 over 2 or 17 over 5. Has to be thirds. Now, look at this here. So you have to know your English. Turning points, that's plural. So you need, there's the 2 values, but the point needs a x as well as a y. Now, how do we do that? We have to determine the corresponding y value and the corresponding x value. So what we're going to do, just a bit of advice. You see there are 2 values there. Always try in mathematics to start with the easy thing first. And what will be easier to substitute? Not the first value you see there. Look here, 1 is e, so substitute 1. Quickly substitute 1 in there. You could actually do it without a calculator. But just to make sure, substitute 1 and also substitute 17 over 3. But be careful when you substitute there. Negative bracket 17 over 3. You don't need to write it down, just do it on the calculator. And those are the 2 corresponding y values. Let's just write them in coordinate form. So there we have 17 over 3. You can even write the decimal version of this down. 400 over 27, write down the decimal version. And now we're going to determine the next point here. And this is the inflection. How do we determine inflection? The second derivative. So go to the first derivative and differentiate that. What do we get? Give you a chance. Negative 6x plus 20. This is now a linear, easy. Let's solve for x, and we get 10 over 3. But remember, point needs an x value as well as a y value. And there's the corresponding y value. So let's write that, as we said, we'll also write that in coordinate form. Now we're ready. I'll take out that system of axes that you prepared for me. So you have it there. And now you see all the points that you have to plot. I've put them in green. It's easy for you to see. Plot the y-intercept, right? So on your y-intercept, y-axis, look for negative 28. Now please, if you count 1, 2, 3, 4, 5 up to 10, don't go off the page. Just change the scale there so that at least you can fit in negative. So maybe instead of counting in ones, you could count in fours. So it's just a little bit of advice there. So put down the point clearly, right? Don't be shy. Make a decent point down for 0 and negative 28. And plot, I want you to plot the y-intercept and the 3x-intercepts. Okay, you've done that. And that is what you should have done. Clearly put down those points clearly there, right? 7, don't be shy. Put a decent point size. The teacher must be able to see the points. The examiner must be able to see it clearly there, right? So you have negative 1, 4, 7, and negative 28. See, you just have a different scale there. But you have got your markings off, and you only put in those points there. That we're not worried about the 3 or the 5 or the negative 2, only the relevant points. So now let's go. Now we need to plot the turning points. Again, plot the easy one first. Which is the easy one? 1 and 36. 1 and negative 36. So there's 1, and I look for negative, so it's somewhere down there. Plot that. And the other one is 17 over 3, which is 5, comma. So it's somewhere there. And then the other point there will be a point. Just get that on the calculator and you get a point approximately somewhere there. So let's plot those points. And there's the one turning point, and there's the other turning point. I see I've already plotted the inflection point, and you can see if I look at, just see a straight line that joins that local maximum and the local minimum. So the inflection point is right there in the middle. Okay. Now, I want to give you a little bit of advice. You see these points here are the intercepts, 3 intercepts and the 1 y-intercept. Now, to distinguish between this, I suggest here by the turning points, put a little circle there. You know, the road, you have a circle, and what do you do with a circle? You mustn't go straight through. You must turn. So this will remind you that if you come here, you must turn. You must make a turn there. So I suggest you draw a small little circle around there. And this is the inflection. You can either put a little cross there, or let's leave it as it is there. Now, I'm going to show you how you can draw these curves using these points. It is recommended that you start from your inflection point. You see, there's my inflection point. Then from this inflection point, go towards that turning. Do you follow? What must I do there? Must I do that? No. That tells me, see, the circle reminds me I have to turn. And there you can see you turn, and that's what you do there. Come try to do that one. That's correct, and that's what you should get. Right? That's a very sober curve there. Go down there, straight down there, and you turn nicely that way. From this one again, there's the inflection. Go through the X there, and then you see where that circle's now reminding you. Don't go up. You have to make a turn there. And if you turn, that is what you would obtain there. So I go there, and I turn, and I go down. And there you've drawn a cubic curve of a cubic function there, right? So from the inflection, go to the turning, and turning means turn. That thing is also reminding you to turn there. Another example, x cubed plus 2x squared minus 4x minus 8. So first of all, y-intercept. What's the y-intercept? Yes, we just expect you to write it down, right? So 0, and don't go and type in 0 cubed plus 2, 0 squared minus. That's extremely embarrassing if you do that. Then we have to determine the x-intercept or intercepts. In this case, we expect at most 3. If you do this, right? And in this case, we notice there are only you only obtain 2, because one of them would be repeated. Okay? So it's only at -2 and 2. So x-intercepts and 1 y-intercept. Then we have to determine the first derivative. Let's find the first derivative. So let's try that. Write it down quickly. Let's check the answer. There's a 3x squared plus. So this is a quadratic. You see, you have a cubic. You end up with a quadratic. Quadratic equation, different techniques. Either factorize, or if it's a bit of a challenge, use your quadratic formula. But if you can do it with your calculator, just use your calculator. Right? And then we obtain now. There's your, if you wanted to use factors, but we're just interested in the critical values. There's the critical value at 2/3 and -2. But it's points, so I need to find the corresponding y value. Which one you're going to substitute again? Not necessarily the first one. Do that one. It's easier. Put that bracket -2, you know, your calculator techniques there. So those are the corresponding values there. You can either give it to us into in this form or that, or you can even write the decimal version down. But this is the exact values. So let's write it in coordinate form. So there I have 2 turning points there. Then what's the other point there? Let's get used to it. That's right, the inflection point. You see, that's plural point, so we expect 2. Point, we expect 1 there. And how do we do that? Find the second derivative. So I take the first derivative, differentiate it. Let's try that. Okay, you ready? There's a 6, and that's a linear. So we see we go from a cubic to a quadratic to a linear. We're going to do that again later. That is a linear, that's easy, and that should just give you negative 2/3. And then we need the corresponding y value. Go to the calculator, and there's the corresponding y value. So there we have our points. Again, let's look at this. We have to plot the y, the x, and the turning. Let's do those three. Always do those ones first. Plot the y and the x-intercepts first. Come. You all ready? This one is not that large, so maybe the -8 can fit in your grid. And there we have those 3 points, right? So maybe you'll get in an exam 1 mark for plotting the intercepts. You won't get 1 mark, 1 mark, 1 mark, right? It's not throwaway marks like that. Now the turning points, again here, try to plot the easy ones first. That one. So there you plot. And what did we suggest about the turning points? Put a little circle where it, you see it must turn it. So you have a little circle around that one. There, and a circle around. Well, that reminds you must turn. You're not going to go straight through it. There's a circle. You obey the traffic rules. You have to turn there. So let's see now. And this is and you can see again the inflection. If I draw a straight line there, that inflection point will lie on that straight line. Now, how do we draw it? Put your pen down on the inflection and go towards the turn. And now you turn. Do you follow? You go there. I mean, that tells you, it reminds you, even if you turn, that's a good reminder there. So you have to turn. So if I do that, that's what I get. Take this one here. From there, you turn. And that's what you get. And there's your cubic equation. Easy peasy. Right? But just be careful. And also, when you put down these points, don't just put down points. You must put down 2 or 2, 0. Put the coordinates down. You cannot expect the examiner to go and count. That's 1 and this is 2. And the examiner must now count 1, 2, 3. You know, put the exact value next. We're not interested in the other values. Just put the relevant ones down there. Right? Normally you get about 3, or sometimes the examiner is generous and he gives you 4 marks for plotting that there. Right? So you'll get a mark for the intercepts, a mark for the turning points, or and then a mark for actually drawing the curve there. Look at the last example. So in this particular one here, chosen this one with a specific reason. Remember the first one we had 3x values, then we had one with 2x intercepts, and now let's look at this one. In this one they might even guide you. Y-intercept, come, easy now. Y-intercept is, don't embarrass yourself, just 0 and -33, right? There should be a law against people who type in 0 plus 0 plus 0, -33, and then wait for the answer there. X-intercepts, let's use our calculator. In this case here, we notice only x equal to 3 is the only root there, right? In this question here, normally they would ask you, show that x equal to 3 is the only root. Turning points, let's find the derivative. There's the derivative again. Remember, cubic, then you get a quadratic. Solve the quadratic. In this case, we get 2 values. Again, we're not surprised to get thirds there because we have 3. You'll be very surprised. I mean, you should be shocked if you don't get thirds there. Then we get the corresponding y values. Either write it in this form or that. You can even write it in decimal form. Then we write down the turning points in coordinate form. Not essential, but it's advisable to do that. Then we have the, what's that other point? Yeah, we have to get used to that one. That's right, right? The inflection point. And how do we find the inflection point again? Differentiate again. So what must I differentiate? That's right, the first derivative. Let's differentiate it, and that gives us 6x plus 4. Easy. And there I end up with -2/3, and a point requires an x and a y. Just always read there. Point single, it's not inflection points, it's inflection point. And there we have the inflection point. Let's focus on the green. It should go quick now, right? I mean, really, if you calculate it correctly, plotting of points for grade 12 should be easy. So we plot our intercepts. In this case, we notice there's a y, but only one x. right? Don't stress there and think you did something wrong. We will encounter problems where we only have one real root. Now let's see now. Again, here you've seen, plot this one. It's easy. Start with a -2 and you plot it, and then you go to the fraction one there, then you plot it. The same here, -2/3, and that shouldn't be much of. So there we have. We've plotted our points there. And now we just put our circles around. That was the one turning point, and that is the other turning point, right? And there's the inflection point. You can see there the inflection point is nicely. That's the one turning point, and I'm not putting the coordinates in here because it's a bit small there. So let's look at that. There's the inflection point. So from the inflection, do I go that way? No. That tells me when I get towards it, I must be prepared to turn. So I make a turn like that, right? And from there, I make a turn, and I make that turn there. And there we have it. And there's our complete curve there. Please remember, don't just put in dots. You can't expect the examiner to count 1, 2, 3. That 3 must be in, or you even write it in coordinate form, right? The turning point you write in coordinate form. Unless this was on a grid, then it's, but you cannot expect the examiner to go and count 1, 2, 3 and know. You must label it correctly. I didn't label the inflection point because it's a bit congested down here. So that's from the inflection, and then you turn from the inflection towards. That's the recommended way to draw curve. Now, as usual, before you actually start with this worksheet, I suggest you go through the previous worked out examples and some of the concepts that was discussed. Take that example, do all the calculations on your own. Don't just look at it, try it. Once you've try all three, then you start. Let's look at what we have here. Question 1. There's an easy one. This one actually they guide you, to show that's a factor. Then you have to factorize, and then you obviously from there you'll get your. Then see, they won't just ask you sketch the graph. There'll be some leading questions to assist you there. There's another one. Determine the coordinates of the turning points, etc. There's another one there. A fifth one, right? Little different, number 5. And you can see I've referenced it to the external examinations there. This was June 2017, and this is February 2016.